Hi guys, Audrey here. So today we're going to talk about sequences. Specifically, we want to talk about finding the general term of sequences. So we have some tips that help us to do this. We've seen two very specific different kinds of sequences. The first is an arithmetic sequence, and that's a sequence that occurs when we're constantly adding the same number over and over again to get from one term to the next. We know that the general term of an arithmetic sequence is a plus n minus 1 times d. Next, we have a geometric sequence, and that's when we're constantly multiplying by the same number to get from one term to the next. And we know that the general term of a geometric sequence is a times r to the n minus 1. Okay, so some other things to look out for when we're trying to find general terms are powers like n squared, n cubed. So that would be like 1 squared, 2 squared, 3 squared, 4 squared, and in factorial. So we're going to keep all of this in mind, and we're going to start by trying to find the general term or the nth term of this sequence right here. Remember, the general term is a term that when I plug in the rank or the location in the sequence, I should get the value. So for the sequence that we're about to do right here, the fourth number is 375 over 5. So when I plug in 4 to my general term, it should spit out 375 over 5. Okay, so let's get started. We have this thing right here. The first thing that we should always check is this geometric or is it arithmetic? Sometimes it's a little bit challenging to do that with fractions. If you don't immediately see it when you have a fraction, a lot of times it's useful to just go and look at the numerator and denominator separately. So we're going to start by looking at the numerator. So a thing to notice in this sequence is that the first two terms are negative, but none of the terms after that are negative. Also, those negatives are specifically given to us in the denominator, so it makes sense to leave them there. So when I'm writing my numerator down, I'm not going to bring the negatives with me. I'm going to leave them in the denominator where they started. So what I have here is 3, 15, 75, 375, 1,875, and so on. So the first thing I'm going to ask myself is it arithmetic? So 15 minus 3 gives me 12, which means to get from 3 to 15, I am adding 12. If I do 15 plus 12, do I get 75? And the answer, not 7, do I get 75, does not equal to 75, which implies that this is not arithmetic. I am not adding the same number over and over again to get from one term to the next. So then the next question is it geometric? Now to see if it's geometric, I want to know what I'm multiplying by. So I'm going to do the ratio of the first two terms instead of the difference. So I'm going to get a 5 there. So I'm doing 3 times 5. 15 times 5, it turns out, is 75. 75 times 5 is 375. And 375 times 5 is 1,875. So this is geometric, which means that we just need to plug into our formula a times r to the n minus 1 for a geometric sequence. My a, remember, is the first term, so this a is 3. My r is what's called the common ratio. It's the number I'm multiplying by to get from one term to the next. So in this case, that's 5. So then we get that the a sub n for the numerator, the general term for the numerator, is 3 times 5 to the n minus 1. Now we want to look at the denominator. So my denominator here, like I said, we are going to include the negatives here because that's where they were included when we started. My denominator, oh my gosh, my denominator is -4, -1, 2, 5, 8, and so on. Again, I'm going to start this the same way. Is it arithmetic? Is it geometric? So let's take a look. Arithmetic would mean that I am adding the same term to get from one thing to the next. So I'm going to do -1 minus -4, which gives me a positive 3. So if I add 3 to -4, I do get -1. Okay, check it out. If I add 3 to -1, I get 2. Plus 3, plus 3, 5 plus 3 is 8. So the answer here is yes, it is arithmetic. So that means I just need to plug into my formula a plus n minus 1 times d for an arithmetic sequence. Again, my a is the first term. Oops. My a is the first term. So a is -4. My d, what's called the common difference, is the number that I'm adding to get from one term to the next. So in this case, it's 3. So my a sub n for the denominator is just -4 plus 3 times n minus 1, which is -4 plus 3n minus 3, which is 3n minus 7, which makes my general term for the entire thing 3 times 5 to the n minus 1 over 3n minus 7. So this is my final answer for the general term here. Okay, so in the next question, we'll do something where something a little bit different happens. So in this one, it was pretty straightforward. We got arithmetic and geometric. Numerator was geometric, denominator was arithmetic. So what happens when that is not the case? All right, so our next sequence, 6 over 8, -24 over 4, 120 over 2, -720 over 1. The first thing that I notice about this sequence is that every other term is negative. Not like the last one where only the first two terms were and then everything was positive. In this case, it's bouncing back and forth or oscillating between positive and negative numbers. That makes this alternating. So in the same way as the last question, this is a fraction, so I'm going to separate it into numerator and denominator, but I'm going to start off by dealing with the fact that it is alternating. So because it's bouncing back and forth between positive and negative, I'm going to need some -1 to some power to deal with that. Well, I want, when I plug in n equals 1, I want a positive 6 over 8. When I plug in 2, I want a -24 over 4. 3 should then be positive, 4 should be back to negative. So in other words, when I plug in even numbers, I want the thing to be negative. So -1 to the power of n isn't going to deal with that. -1 squared is positive. -1 to the 4th is positive. So I could either add or subtract a 1 here. In +1 or in -1, either will work. So that deals with the alternating bit. So now I'm going to look at the numerator. I already dealt with the alternating bit. I'm not thinking about negatives anymore. So I'm going to not look at those negatives at all when I'm writing down the numbers in my numerator. Okay, so the first thing I want to do is check whether this thing right here is arithmetic or geometric. When I look at it, it kind of is obviously not either. Those numbers get really big really fast. So like I'm clearly not adding the same thing or multiplying by the same thing. So we can say clearly not arithmetic or geometric. But what I just said, those numbers get big really fast. That's a sign that maybe we have a factorial happening. So the numbers get big really fast. Maybe factorial. Okay, so a good plan in this case would be to write down the sequence in factorial so we can see if this is a factorial and how it's happening. So in factorial here is equal to 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720, and so on. Being comfortable with this or knowing how to calculate these things is going to be useful. So what we see is, hey, look, some of the numbers, 6, 24, 120, 720, are the numbers from my factorial sequence. Yay! But we also see that we did not use the first two numbers here. So there are two ways that we could think about this. We could be like, hey, look, the numbers in our numerator are factorials, but they're being shifted to the right by 2. Which means that the general term of my numerator is not going to be in factorial, it's going to be in +2 factorial for that shift that happened. Now, if that's a little bit confusing to you, another thing that we can do that's really useful for factorials, especially when the factorials aren't just one after the other like they are here, is to rewrite the numerator in terms of factorials. So I could say that the numerator is equal, that's 3 factorial. Actually, let's do this in the galaxy pen. So this is 3 factorial, 4 factorial, 5 factorial, 6 factorial, and so on. So what we can see is when we look at 3, 4, 5, 6, to get from one number to the next, I'm just adding 1. So I can think about that without the factorial signs as an arithmetic sequence where my A is equal to 3 and my R, not my R because it's arithmetic, so my D, my common difference, is equal to 1. And when I plug this into the formula, A plus n minus 1 times D, I get 3 plus n minus 1 times 1, which is 3 plus n minus 1, which is n plus 2. Notice the same n plus 2 that we got over there. We had ignored the factorial signs to get that, so now we can add them. And we end up with the same thing that we got when we thought about it just being a shift to the right. So if you have trouble understanding how those shifts work, you can always think about it as an arithmetic sequence like that. So we have n plus 2 factorial for the numerator, and now we want to look at the denominator. So my denominator here was 8, 4, 2, 1, ... And it turns out that this is actually pretty straightforward because I can pretty much straight up see that I'm just multiplying by a half each time. If you don't see that, you can go through the checks and be like, hey, look, 8 minus 4 is 4, but 4 minus 4 is not 2. So it's not arithmetic. 4 divided by 8 is a half. Oh, hey, look, it is geometric. That works. So this is geometric with my A equal to 8 and my R equal to 1/2, which means that my A sub n for the denominator is 8 times 1/2 to the n minus 1, which means that for the whole sequence, when we put it together, A sub n, we dealt with the alternating part, -1 to the n plus 1. Our numerator was n plus 2 factorial, and our denominator was 8 times 1/2 to the n minus 1 for my final answer here. Okay, so that's our general term for this sequence. So today we've dealt with geometric sequences, arithmetic sequences, and we saw some factorials show up. I'm going to make another video. So in the next video, you can check it out. We'll see when the powers happen. So when we have like n squared or n cubed and the other things that can happen. That's all for today. Bye, guys.